like every time I see like what is done and what the hell are you doing. The main thing is I was studying about solutions. So from the solution chapter, one thing I noticed that there are many numericals I cannot even which I can't complete. In fact, I am talking about completing, even I cannot start it, cannot even touch it. So I think I have to repeat the Raoult's law, the Dalton's law, and Henry's law. I have to repeat individually each one. So today is the day which will be invested in those three topics: Raoult's law, Henry's law, uh, Raoult's law, Henry's law, and thirdly we have Dalton's law. Raoult's law, Henry's law, and Dalton's law. These three laws. After I write the after I write the mathematical representations and also the explanation of it, and also the application in real life if possible, and also the application in various numericals which can come in exam. I'm going to dictate the important equations or important rules that which I understood while solving the MCQs. Oh, this is another coffee one. Oh, I have another problem now, which is molar depression constant. So first of all, like these things have no importance. Like, what is the definition of solution? What is homogeneous? What is heterogeneous? And brass, Kusan, copper plus zinc, bronze, Kusan, copper plus tin. Bronze is used to make bronze coin. We have heard it before. But brass is used to make utensils like dishes, petal, যেটাকে বলে. We get solution when we mix solute and solvent. One thing we have to remember that in a solution, the component which is let's say in a binary solution, the component which is present in the less amount is known as the solute, while on the other side the component which is present in maximum amount is called solvent. Solute plus solvent is a solution. For an example, if we take that salt plus water, then here solute is salt because it is present in the lesser quantity, and water is a solvent because it is present in the largest quantity. Now we have what is known as a binary solution. Then we have solution, three types: solid solution, liquid solution, gaseous solution. All these things are not important, so I'm gonna skip. And when we come into the solubility, the dilute solution and the concentration. Now concentration can be expressed in two ways: qualitatively and quantitatively. From then we're gonna rebranch the quantitative branch, if you can understand. Then the quantitative description of concentration of a solution can be further described as many more ways. Now the ways are mass percentage, which is denoted by W by W; the volume percentage, which is denoted by V by V; the mass by volume percentage, which is denoted by W by V. W means mass and V means volume. Then we have parts per million. Parts per million. So 1 million means we have 6 zeros beside 1. 1 million means 10 to the power 6 simply. And then we have mole fraction, and then mole fraction is denoted by chi, chi. And then at last we have molarity, and then another thing we had, which is molality. Now one thing important comes from here. Molarity means number of moles of solute by volume of the solution. And then molality, L, it means number of moles of solute by volume of the solvent in which the solute is dissolved in order to form the solution. Then we have the descriptions of mass percentage, volume percentage, mass by volume percentage. I have not seen any numericals. I have not seen numericals coming from mass by volume percentage. Maximum things come from the mass percentage, W by W, but V by V or W by V is not too common in the numericals as long as I have seen. Next we have the parts per million, which is in short form known as ppm. Now this is also underrated as long as I know. And then we have mole fraction, which is known as the which is represented or is denoted by the Greek letter chi, chi. It is like x, like that. Then we, in case of the binary solution, only two components are present. One is solute, another is solvent. XA, chi A equals to NA by NA plus NB, whereas chi B equals to NB by NA plus NB. Now if we calculate chi A plus chi B, we will get 1. So we can write that the summation of all the components in a solution, the summation of the mole fractions of all the components in a solution equal to 1. Done. Now then we have molarity, which is represented by capital M. Another very good thing we have to remember, good conversion we have to remember: 1 liter equals 1 decimeter cube. 1 liter equal to 1 decimeter cube. Very important, so I have to mark it. One liter equal to 1 demi cube, 1 decimeter cube. Now this is called the molarity. If we talk about the unit, then we will get mole per liters. In case of molarity, M, capital M. Now we come to small m, which is molality. The expression is, molarity is defined as the number of moles of solute per kg of the solvent by mass of the solvent. Molality equals to, what have I said it earlier? I just forgot. Okay, let's clear it. Molality, which is denoted by small m, equals to number of moles of solute, which comes in the numerator, which is divided by the the mass of the solvent in which it is dissolved. It comes in the denominator, forming the solution. Now this small m is known as a molal, MOLAL, 1 molal solution of KCl. What is the meaning of this? Now at 1 mole of KCl is dissolved in 1 kg of water. Simply everywhere is 1 and 1 and 1. So 1 molar solution of KCl, it means 1 mole of KCl is dissolved in 1 kg of water, which is forming this solution called 1m or 1 molar solution of KCl. Okay, now let's talk about the unit. Unit is small m. Small m is also the unit of molality, and capital M is the representation of molarity and also the unit of molarity. And in case of molarity also, small m is the representation of molality and also the unit of molality. Another unit you can say mole per kg in case of molality. Oh, molarity is temperature dependent because volume depends on temperature. Whereas molality is temperature independent because mass does not depend on temperature. Now, so here we see that temperature is directly proportional to volume, is indirectly proportional to m, capital M, molarity. Molarity is dependent on temperature. Oh my god, then we have Le Chatelier's principle. Oh, the condition shifts in such a way that it opposes the change. OMG, I forgot all these things, man. I have to repeat this again and again and again, man. Oh, dissolution means solutes entering the solution, and crystallization means solutes leaving the solution. When bonds form, energy release. When bonds break, energy is required. Energy is absorbed. So energy release means an exothermic reaction, and energy break and bonds break means taking energy or absorbing energy, which is an endothermic process. Another very good conversion we have seen so far is 1 atm equals to 1.01 into 10 to the power 5 Pascal PA. Now this is seen in case of pressure. These are the atm, atm and Pascal are the units of pressure. So it is a conversion in case of pressure. And then comes the equilibrium parts while evaporation, while conducting evaporation or vaporization in a closed container. And then you come to the Raoult's law. Oh my god, the graph between the vapor pressure and the mole fraction TAC, and the P total is formed by P1 plus P2. One thing I realized that I have to repeat this, man. I have to repeat this. Ideal solution. Oh, in case of ideal solution, the delta H is equals to 0 and delta B is equals to 0 and delta S is not equal to 0 and delta G is not equal to 0. Remember that. So equal to 0 are two variables which are delta H and delta V, and not equal to 0 are another two variables which are delta S and delta G, capital S, capital G. Then another important thing we have the positive deviation, where solute interaction bond is where solute and solvent AA and BB interaction bonding is stronger than in case of solute and solvent, which is AB. As an example, we have ethanol plus acetone. Very important example I have seen in various MCQs. In many MCQs, this positive deviation and ethanol plus acetone as an example. Will I explain this? Okay, when ethanol and acetone, when ethanol is in the solution, when ethanol alone is kept in the beaker or in the container, then we see hydrogen bonding to form between the molecules of ethanol. But when acetone enters the solution of pure ethanol, the solution is forming, and due to the entry of acetone into the solution, the hydrogen bonds present between the molecules of ethanol breaks, which makes it easier for the vaporization of ethanol to happen. So the vapor pressure increases, and that is why we get a positive deviation in the graph. The opposite thing goes for the negative deviation, but sadly I have not till seen any questions from negative deviation. If I say by short, in the negative deviation, the AB bond is stronger than AA and AB. If I talk about ideal solution, we will get that the AA and BB solution is strong as much strong as the interaction bonding between A and B. AABB is equal to AB bond interaction. Example of maximum boiling azeotropes is water plus nitric acid. Now there are the conversions between Raoult's law and Dalton's law, from Dalton's law to Raoult's law, and the usage of one law into the another